Okay, I'm Driggs, and I do work in optimization, especially with applications to imaging problems. And in the past couple years, this really beautiful theory has emerged studying the continuous time limits of optimization algorithms. And because it fits so well with the theme of these talks, I thought I would give a brief survey of these results. So our problem setting is that we would like to minimize a convex function f. And throughout the talk, we'll assume f is L smooth and mu strongly convex. And if I want to remove those assumptions, I'll just set L or mu equal to 0. And these assumptions are equivalent to these bounds being satisfied for a first-order approximation of our function f. And this problem is very popular right now, but it's by no means a new problem. And it's been studied for hundreds of years. So there are a lot of methods for solving this problem. The most popular are gradient descent and Nesterov's accelerated gradient descent. And the ideas behind these algorithms are very simple. So we want to find the minimum of this function. We'll just go downhill until we get to the minimum. And Nesterov adds in this extrapolation at each step and then performs gradient descent using that extrapolated point. And we get a faster algorithm. And then there's also a third popular algorithm, Poljac's heavy ball method. And this method is the same as gradient descent, but we add a momentum term. And we head further in the direction as predicted by a previous iterate. And this will also give us acceleration in some cases. So we can compare all three of these algorithms in terms of their convergence rates. Gradient descent without strong convexity converges like 1 over k, where k is the number of iterations we've taken. And Nesterov's accelerated gradient descent, true to its name, converges like 1 over k squared, so it converges at a faster rate. And Poljac's heavy ball method is a bit more complicated, so it converges without strong convexity like 1 over k, but with strong convexity, it converges at a linear rate that's comparable to Nesterov's accelerated gradient descent method. Okay, so these are three commonly used algorithms for optimization, but we would like more algorithms, and we would like more accelerated algorithms. And Nesterov's accelerated gradient descent, the intuition underlying this algorithm is notoriously difficult to generalize. But Poljac's heavy ball gives us some intuition that we can work with. So Poljak named his algorithm the heavy ball method because it comes from a discretization of an ODE. And this ODE describes a mass in a potential field with friction. So it's a very simple intuition. If we want to get to the bottom of a hill, we can just roll a ball down the hill, and we'll eventually get there. And if we discretize this ODE using a combination of forward and backward Euler, then we can recover Poljac's heavy ball method. So these are the origins of Poljac's heavy ball. And these ideas, unlike Nesterov's ideas, can be generalized. So if we work backwards with Nesterov's accelerated gradient descent, we can take the continuous time limit of this algorithm by sending the step size to 0, and we obtain an ordinary differential equation that's much like Poljac's heavy ball ODE. So there's something fundamental about these types of dynamics in optimization problems. And once we're in this continuous time setting, we can also study convergence rates in continuous time. So for Nesterov's accelerated gradient descent, we get convergence in continuous time like t squared, which is reminiscent of the discrete time algorithm that converges like 1 over k squared. So this acceleration is very natural in the continuous time setting, whereas it requires a sort of counterintuitive approach to achieve it in the discrete time setting. So we want to see if we can use these ideas to develop new accelerated algorithms. And we can do this with additional assumptions on f. So if we have higher order smoothness assumptions on f, we can study a different ODE and prove convergence rates that are accelerated for higher order gradient methods. And these are all in continuous time. but it shows that these ideas are very natural in continuous time. And a paper published earlier this year takes this idea one step further, and we can rewrite Poiac's heavy ball ODE as a Hamiltonian system here and introduce a kinetic energy function, k. So for the original Poiac's ODE, the k is the identity, but using intuition from the theory of ODEs, we can choose k in a better way to obtain better convergence results. So just to see how this intuition works, consider the example f is a quadratic, so it's the inner product of ax and x. And if we choose k to be the same as f but using A inverse, we obtain a Hamiltonian system that's independent of A, which means all convergence rates are independent of A. So when normally convergence would depend on the condition number of this matrix A, we can remove that dependence by choosing k appropriately. And to generalize this idea, if we choose k to be the convex conjugate or something related to f, then we can obtain a conditioned system and linear convergence results where this previously was thought to be impossible. So if we only have access to the function f, then we cannot do better in general. We cannot get a linear convergence rate. But if we also have this k and we choose it appropriately, we can get linear convergence rates in situations where it was previously impossible. And so far, we've only talked about the continuous time setting. So to get actual algorithms out of this approach, we need a smart way to discretize these ODEs, like we did for the Poiac's heavy ball method, that maintains these accelerated convergence rates. And this is where I'll go next in my talk. So we get these accelerated convergence rates very naturally in continuous time, but we don't know if these lead to a stable algorithm or if it leads to an accelerated algorithm at all if we apply a discretization. As we saw with Poiac's heavy ball, applying backward Euler and forward Euler does not give us an accelerated rate. So Poiac's heavy ball converges like 1 over k. So we lose this accelerated rate upon discretization. But we can also apply forward and backward Euler in a different way, and we obtain a new algorithm that converges faster than gradient descent, but it's asymptotically unstable. So we might converge to the solution very quickly, but if we run this algorithm too long, it'll diverge, and we don't know where it's going. So this algorithm is also not useful. So the question is, what type of discretizations give us accelerated algorithms that are also stable? And this is an ongoing area of research, but a lot of heuristic discretizations work, so things like combining Crank-Nicholson with backward Euler, and also symplectic integrators, so things like the leapfrog method, are natural choices for these types of systems because they preserve quantities in Hamiltonian systems. And these numerically have shown to work, but we still need a theoretical basis for their convergence guarantees. And very recently, Runge-Kutta integrators have been shown to produce stable and accelerated methods. And the algorithms that result from these discretizations are often have even faster convergence rates than Nesterov's accelerated gradient descent, given more information about the function that we're optimizing. And another interesting thing to consider, Nesterov's method does not correspond to a naive integrator. So figuring out why Nesterov's method is accelerated and fitting that within this theory is another ongoing area of research. So just to leave you with some open questions, it would be very nice to have a best practice for discretizing these ODEs. So we have ideas that work and we have ideas that don't work, but there's no reason why certain integrators work and certain integrators don't. Also, it's much more common today with huge data sets to not be able to compute the gradient of f, but instead only having an estimate of the gradient, whether this is through stochastic optimization or through incremental gradient methods. This is a very common problem, so it'd be interesting to see how this theory generalizes to this setting as well. And another question, we've looked at a lot of different ODEs that produce good algorithms, but are there other types of ODEs that would give different algorithms that are also accelerated? And this is particularly interesting for stochastic gradient descent. So maybe instead of studying ODEs, for this setting, we should study stochastic differential equations and see how those fit within the framework of this theory. Okay, that's all I wanted to say, so I'll open up to questions now. Thanks for listening.
Right, 10 questions. We have 2 here.
All right. Your system is not really Hamiltonian.
Okay.
Unless you are taking eta equal to 0, and then, of course, it will not converge to anything.
Okay.
It is what is known as conformal Hamiltonian system. And symplectic methods, for example, don't work for conformal Hamiltonian systems. There is only one method I know about which was designed for this, of McLaughlin and Quispel.
Okay.
So you should have a look at it.
Okay, that sounds great. Thank you.
One question, I think.
It was the same.
Any more questions?
Yes, Rob.
So when you were talking about the, so if you use the conjugate, then you can remove the conditioning number on A. Does this look like a preconditioned method when you start discretizing it? Do they look the same, or is it not simply a general?
It doesn't look naively the same, but there are some similarities. So if we use this convex conjugate as K in the system I showed before, every step with the gradient looks sort of, if we're optimizing over a quadratic, the gradient, or this function is very skinny and steep intuitively. And then the convex conjugate then is fatter and deeper. And so by interplaying the two of these functions, then we get something that looks closer to a well-conditioned quadratic problem that's easier to optimize. But that's really the only connection that I've seen. Yes.
Okay, another question. So you say that Nesterov's method doesn't fit into this pattern.
Okay.
And it is obvious why it doesn't fit, because it is non-autonomous. You have this k minus 2 over k plus 1. But now suppose that you allow your eta to depend on time.
Okay.
So you have a non-autonomous conformal Hamiltonian system, and systems like this are known. And then you should be able to incorporate changes over time of this acceleration parameter.
Okay, that's very interesting. Yeah, it's often the case that eta does depend on k. So that's a good insight. I'd love to talk to you after about this.
All right.
Okay.
In the interest of time, we should probably move on to the next talk. And thanks, Derek, again.
Thank you.